By the way, in the lab, you're not using inductors. Sorry. I tried to do it. The trouble with finding an inductor is that you need the wire big enough so that resistance is not of any importance. And all the coils I had, I couldn't find one with a large enough inductance and a small enough resistance. So ultimately, inductors not make it into the lab. Relativity, special relativity more specifically. When I say special relativity, we're talking about reference frames with no acceleration. General relativity is when you get into accelerating reference frames. But we're going to start out with the thought experiment that I introduced 2 weeks ago, whatever it was. I have a box that's zipping along at some speed v. It sends up a light because there is a horizontal motion, that the light does have a horizontal component to it. In other words, light's going to hit this mirrored ceiling and then bounce back and get into the box again. The distance from here to here will make h. So we'll call this the lab frame. And then the rest frame, which we can also call the box frame. I basically have the box there, distance h away from the mirror, that doesn't change. It's going to shine light up, light's going to come up, hit the mirror, bounce back, or straight through the box. And just as a refresher, if the speed of light is the same in both cases, well, regardless of whether the speed of light is the same in both cases, in which case is the light traveling a greater distance?
Case 1.
All right, so if the speed is the same in both cases, and this is a longer distance, which has the longer time?
Intuitively, we would think case 1.
And it should be. I mean, intuitively, you would say, well, it's the same amount of time for it to go back and forth, at least most intuitions, but hopefully as a physicist, you're starting to get the hang that time is not the same for both, and that was discussed last time. So, let's take a look at the relationship between the time here and the time here. Now, the time here, I'm going to cleverly label t. You can talk to me afterwards or send me an email if you're not quite sure where I got that letter from, but you know, we'll just go with it for right now. This one right here, we're going to label t sub p. The p stands for proper. This is the proper time. Proper time is the time in the reference frame that is not moving. So, in essence, because we're in the box frame, in the box frame, the box is not moving. This is why this is proper time. This is not called, it's not called improper time, it's just called time. So in this particular case, I know that the speed is distance over time. Well, what's the distance that the light travels? Over t sub b, so distance over time. In the top case right here, I know my vertical leg is h. My horizontal leg is going to be 1/2 vt, because in that whatever time it takes, it travels some distance vt. So the time it takes for the light to get to the top is half of that. So my hypotenuse here, the Pythagorean theorem, is 1/2 vt squared plus h squared. So therefore, what is the distance traveled? Reason is over there. So we have 2 times the square root of
1/2 vt squared plus h squared
divided by 2. C is the same for both. This was the assumption that Einstein made. H is the same for both because, well, I set up the problem to be that way. So, well, I want to get rid of H as something that manufactured, whatever rule I come up with should not depend upon distances vertical or perpendicular to the motion. So I'm going to solve for H in this formula and plug it into here. So H is 1/2 C T sub P. So if I plug that in for H, and I'm going to go ahead and multiply by T and divide by 2 just to get rid of my fractions and that coefficient there. So I have 1/2 CT is equal to the square root of 1/2 VT quantity squared plus 1/2 CTP squared. Of course, I want to square both sides to get rid of my radical. So I have 1/2 CT squared is equal to 1/2 VT squared plus 1/2 CT sub P squared. Now I got 1/2 squared in every term. I can just get rid of it. Multiply everything by 4. The 1/2s go away. And I'm left with C squared T squared is equal to V squared T squared plus C squared TP squared. So I'm trying to find a relationship between T and TP. And so let's get all the terms with T on it on one side and all the terms with the proper time on the other. So I have C squared T squared minus V squared T squared is equal to C squared TP squared. Factor out the T squared. So I have C squared minus V squared times T squared is equal to C squared TP squared. I'm going to isolate T, so let's divide by the coefficient. So I have T squared is equal to C squared over C squared minus V squared times TP squared. So right at this point, it's very clear that there is a mathematically different relationship between T and TP, or sorry, we word that T and TP are not the same thing because I got this coefficient right here. So T is equal to the square root of C squared over C squared minus V squared times TP. And what I have under the radical right here is not a traditional form of it, although it does pop up enough, but it's not the standard form of it. So I'm basically going to take this fraction, I can multiply top and bottom by 1 over C squared. So let's squeeze that in here, so times 1 over C squared times 1 over C squared. And so what I get is the square root of 1 over 1 minus V squared over C squared times dt, which is equal to 1 over the square root of 1 minus V squared over C squared times TP. Sometimes it's written as TP over the square root of 1 minus V squared over C squared. But I wrote it the first form for a reason, give people a chance to catch up, and then talk about shorthand and implications. All right. Shorthand. V over C shows up enough. So they, of course, came up with another letter to represent that. So this beta is equal to V over C. That is a lowercase beta. Beta. So generally, when you talk about the speed of things, when you start talking about relativistic speeds, we're talking about things as a fraction of the speed of light. I mean, it could give you, it's traveling at 200,000 meters per second, or sorry, 200 billion meters per second, or I could just say beta is equal to 0.667. So it's traveling at a speed such that beta is 0.5, means you're traveling at half the speed of light. Now, what I have over there, my coefficient of my proper time, in essence, I have 1 over the square root of 1 minus beta squared. This is known as the Lorentz factor. The one who got so close to actually coming up with special relativity. And they're represented by a gamma, a lowercase gamma. So let's do a little calculator exercise here. So when beta is 0.1, what is gamma? When you have an answer, just shout it out.
1.005.
All right. So not a whole lot of difference. Usually beta is equal to 0.1 is when physicists start to actually take relativistic effects into account. But you're off by 0.5% if you don't. Beta is equal to 0.6.
So got that.
You got the same thing? Okay.
Wait, what do you mean when you say you would be off by 0.5%? Like if we were calculating velocity of your time?
Time would be off by 0.5% because the time that would be measured separately is equal to, in this case, 1.005 times the proper time. So, if it were just plain old 1, they would be equal to the same thing, but we're off of 1 by 0.5%. All right, so now we there starts to be a noticeable difference there. And so when beta is 0.994, let me double check, make sure that's the number I want. Okay, 0.9952.
$10.218.
7.218?
No, 10.218.
10.218?
Yeah.
There we got confirmation?
Yep.
All right. So now we are a very significant difference between the two. So if I were traveling at 0.9952 times the speed of light, for every month I aged, people left behind on Earth, sorry, reword that, 0.9952 times the speed of light relative to Earth. For every month I aged, people on Earth would age 10.218 months. This is not a perception thing. This is biologically, they would age differently. If I had an identical twin, conjoined so that our births were pretty much the exact same time, we would no longer be the same age. So 1905, Einstein comes out with his paper with these predictions.
Did you call it time dilation?
And it's called time dilation. Did he call it that? Presumably whatever the German equivalent is. Let's take this one step further. The twin paradox. Earth, rocket, planet X. So I said if I got in the rocket and I went away and then I came back, and I'm gone for 1 year my time. I'm older by a year. I'm gonna write that slightly differently there. So I age 1 year. What I'm claiming is that people on Earth would have aged 10.218 years if I'm traveling at that speed. But the trouble is, this is from the Earth's point of view. From the Earth's point of view, it's at rest, and it's the rocket that's zipping along. But from the rocket's point of view, the rocket's at rest, and the Earth is zipping there and coming back, and then planet X is zipping there and going back. So in this scenario, the rocket is moving, but in this scenario, the Earth is moving. So here, the rest frame is the rocket. So TP is 1 year, but here, TP is equal to 1 year. Only one of them can be right. This is known as the twin paradox. There's a resolution to it. So what I'm asking you, what's the difference besides perspective? One is from the Earth's point of view, the other one is from the rocket's point of view. What is the difference between these two scenarios?
The reference frames?
Besides that? If the reference frame is the only difference, then the people in the rocket should have aged 10 years, and the other one, people in the Earth should have aged 1 year, and the universe would implode because of time contradictions.
Proper time?
Pardon?
The proper time?
It's think more physical. Physically, what is different between these two scenarios?
Is it the speed at which each of them is traveling?
They would both agree on the same speed. They just disagree what's traveling that speed. So in this case, beta from the rocket's point of view, beta from the Earth is 0.9952, and from planet X. They agree upon the speed. They just disagree with what's traveling at that speed.
So in one scenario, the rocket is traveling, and in the other scenario, the planets are traveling?
Yes. So,
Is that the difference?
but no, well, that's just the different reference frame. Let's do it this way. All right, so we got a door opening over there. I'm traveling towards it, or the door's traveling towards me, depends on the point of view. So from the door's point of view, I'm traveling it in at, let's just say, 1 mile per hour. From my point of view, the door's coming at me at 1 mile per hour. Any questions about that? All right, so now, I'm traveling, let's assume from the door's point of view, I'm going to hit it at 1 mile per hour. And now it's going away from me at 1 mile per hour. Think about what's involved in those situations. There was something with direction, depends on how you want to work that in. I'm heading towards the door. From my point of view, the door's coming at me, and now the door's going away from me. From the door's point of view, I'm heading towards it, and now I'm heading away from it. What did the door feel in those two scenarios? Well, Mario's right here, I'll do it towards Mario. We'll have to do a reference frame thing here. I'm not gonna run at you.
Gravitational force?
Let's not complicate it with that. That's what general relativity kicks in. What did you feel? Did you feel yourself when you turned around?
Not really,
Why not?
no force.
Ultimately. That's the difference in these scenarios. In this scenario, the people on Earth are not experiencing any of that external forces that are required to turn around. It's just a point of view. Here, the rocket does experience forces. It does accelerate. That is a primary difference between these two situations. In this situation, the Earth actually does, the rocket actually experiences external forces. Here, the Earth does not. That is the big, huge difference between these two scenarios, and why the people in the rocket will age 1 year. And the people on Earth will age 10.218 years. There's a fundamental difference between it. Now granted, the background for why does the external force cause this difference, I'm not getting into that. But just want you to realize that there is a fundamental difference.